we have a very interesting talk next from Flavio. So Flavio is already there and he has answered a question. So I'll just give a brief introduction to Flavio. So Flavio is going to talk on inception of fog and edge computing because he's one of the pioneers on fog and edge computing. So I'll give a very brief intro to Flavio. Flavio Bonomi is the founder and CTO of Nebbiolo Technologies, a startup active in the domain of IoT with particular focus on industrial automation. Previously, Flavio was a Cisco Fellow, Vice President and Head of Advanced Architecture and Research Organization at Cisco in San Jose, California. At Cisco, Flavio was co-leading the vision and technology direction of Cisco's IoT initiative. Before joining Cisco in 1999, Flavio was at AT&T Bell Labs. So Flavio, we are privileged to have you talk in this school. So I invite you to go ahead and give your talk.
Thank you. Thank you for the nice introduction and for the invitation. I see some good old friends here, Adam and Tao and others. Are you seeing my presentation here? Does it show?
No, it's not coming through.
Can you stop and reshare again, Flavio?
Yeah, because here it tells me that I am sharing. Okay. You're screen sharing. Maybe it's
there you go.
Yes,
that's it.
You got it? Yeah, I'm probably the most distant from California here. Good evening, good morning, everybody. Today's talk is about the history, fog and edge computing, but also the present journey that continues to manifest the original vision, the mission critical edge computing. I will do a little bit of revisiting of the history of where we came from 2010 onwards, with many of you witnessing that effort, the ups and downs and the suffering of pioneers. And then we'll really stress that fog computing is really originally foreseen as what we now call mission critical edge. So the two are really coming together in terminology, and we have to really strive to manifest this vision into reality. And I'll talk a little bit about what is happening in industrial, the relationship between edge, mission critical edge, and 5G, 6G, and then a little bit on automotive, on the automotive use case. If I have time, I'll talk about the challenges remaining. But first, a brief introduction, just a correction. From Cisco, where we started this whole effort around 2010, I moved to Nebbiolo Technologies, where I was the founder and CEO, but I'm not the founder. I'm still the founder, but I'm not the CEO, and I'm not part of Nebbiolo any longer. Although Nebbiolo manifested an important effort to apply fog and edge computing in the industrial automation space. Right now, I'm working with Lynx Software as advisor to the board, really working on the mission critical edge part from the virtualization perspective. This is my present affiliation. This picture shows you a little bit of the history from the 2011 time frame, where we foresaw the coming of the fog. We didn't know when it would come, but it is coming, and it is taking probably longer, but it's such a broad movement that I think it's worth the wait. So we saw this as the next paradigm shift, and Tao, Adam, and so on participated in those efforts. there was a day in 2010 when the name fog computing landed on this topic. And it's due to this lady in the middle. I'm here on the right side at the Monterey Bay Aquarium Research Institute, where I gave a talk, and there was a lot of cloud and fog and sensors in the talk. And at the end, she said, you should stop talking about cloud computing. You should talk about fog, because it's cloud brought down to the ground, close to the ground. And I protested for 10 minutes. And then I started using the name, and I continued to use it for a few years. That's the day. But what is really behind the effort is the work at Cisco in understanding the connected vehicle world, the evolution of the electronics inside the cars, and intelligent transportation, as well as smart grid. Those were the two main activities at Cisco at that time, and it became clear that there was a need for a distribution of computing that was much more prominent, with some of the same features that cloud computing brought to the world. And you see here the car is a fog node in motion on four wheels, and it requires support from the intelligent infrastructure. So fog nodes at the roadside, and then fog nodes supporting the cellular infrastructure, and so on. So we saw all these coming, and we pursued some of these verticals at Cisco. And I think Tao was in the connected vehicle initiative for a while. So this is, in fact, all coming to life progressively. The car is evolving. We'll see that in a fog edge, mission critical edge way, and the telco edge is preparing to support intelligent transportation. And we see movement in smart grid towards consolidation, virtualization, and fog edge models. In this picture, we see the history of fog moving to edge from 2010 to the 2015 time, with the open fog activities, where Cisco was one of the drivers. And then progressively, the appearance of the edge computing name more and more. There's some politics and marketing behind this transition, but now we are in the time and the age of edge computing. But what is very important is to remember that the full power of this movement to the edge will be achieved when we look at the mission critical edge fully, which was, as I'll describe, core in the original vision. So the next is mission critical edge. Right now we are at the age of the edge computing. And in fact, I'll go to the next slide that will bring that to more clarity. Fog and edge, in our idea, the original fog was not just moving resources, computing resources close to the edge, but was really bringing together requirements coming from the IT world, the virtualization, security, and networking, and data activities, together with the real-time safety and security, and even physical security typical of embedded systems and of OT domains. This is where the two worlds, IT and OT, converge, and this was always at the core of our vision from day one. And this is a little loaded here, but it has all the elements that went into this original fog vision, which I would say is corresponding to what now we call mission critical edge. It's not just edge, but it's edge that is responding to the needs, as I said, of the OT space. First, virtualization that is capable of mixed criticality on the same multi-core system, so that we can have real-time and non-real-time activities, strong security and partitioning, and also safety capability, safety certifiability of some of the stack. Second is the networking. Again, is not just Wi-Fi, the 3G, 4G, and Ethernet, but is really looking at mission critical networking. TSN, time sensitive networking, is the evolution of Ethernet in the real time domain, and 5G and 5G private, and now 6G is the manifestation of a more deterministic wireless technology needed for this space. The next point is the data distribution and analytics core of this manifestation of computing resources at the edge. And here there's a lot to say. I will not dwell on this very much, but Tao talked about this edge AI. We have to remember that edge AI needs to become mission critical, and we are not there. Many of the AI technologies are stochastic, and they are not certifiable. There's a long journey there, but we need to go to mission critical data management and analytics as well. Fundamental to this vision is the concept of asset management and orchestration from a centralized or federated environment, because we need to be able to see a distributed set of nodes collaborating, sharing, and managed in a unified way. And this is where we are seeing containerization and Kubernetes becoming very relevant. Security is fundamental. And then the last point is the ultimate goal is to have, with the real-time capabilities, safety capabilities, is fundamental to see the ability to orchestrate multiple machines, control multiple machines from a point of view that is one step above, one step higher. And this is going to achieve much better results in control, much better efficiency, and so forth. Now, here we dwell on the mission critical virtualization. This is why I am working at this moment with Lynx Software, a company that is providing one of the best software technologies for virtualization, mission critical virtualization, applied to defense and aerospace, and now coming into industrial, automotive, and other applications. Here we want to achieve physical separation, hard real-time and non-real-time virtualization of the hardware, basically, virtual boards, machine-based and virtual machine-based virtualization that also is combined with a more lightweight containerization that is orchestrated and potentially safety certifiable. So these are the key elements making up a system that can be called mission critical. It's the security, the real time, the determinism in the behavior, and the safety certifiability. So that you can bring together on the same multi-core that needs to be hardware-wise prepared for this. You bring together mixed criticality applications that can interwork and can enrich each other and can close the loop towards control with a much higher intelligence than we are seeing today. So this is the big picture that, if you think about deeply, is also needed for the 5G, 6G infrastructure. So that, and we'll see that soon. By the way, computing is finally starting to show its mission critical behavior or qualities with the work by Intel that is coming out with SKUs like Elkhart Lake Tiger Lake, and others that are safety certifiable at these levels of certification, SEAL 2 and SEAL 3 capable. They brought in a technology from Italy that is providing this safety island, complementing all the other resources, monitoring the resources. And it really also, they brought in what is called time coordinated computing, so that the time synchronization goes into the CPUs, as well as the time sensitive networking, so that you can have a synchronized computing distributed to other computing that are also running on the same absolute clocks. So this is happening. These are very powerful products, and we need those to achieve the ultimate goal of fog computing or mission critical edge. Now, in terms of the networking, you guys are probably much more active than I am on this topic at this moment, particularly the 5G. We are seeing the promises coming to life of 5G. Unfortunately, from the talk by Tao, it looks like, but this is not new, some of the promises of 5G become the promises of 6G. And what is not realized in 6G will be into 7G. I'm a little frustrated by the fact that some of these determinism and ultra reliable low latency 5G may not be appearing under the 5G term, but it will be delayed or arrive at the 6G time. I hope we'll have enough features as promised to be able to apply and achieve important successes in the mission critical edge using 5G. So this is fundamental. Sorry, this is going. It's very important that we see the best of 5G coming to life in this perspective. The other one is the wire technologies. TSN is very important here, and is very important, more close to the machines, but is also feeding important features into the 5G standards. So these are the two technologies that will interplay for the future of mission critical edge. One of the big goals of this continuum of computing with mission criticality as well is the ability to create this behavior where sensors are monitored, decisions are taken, and control is applied in hierarchical loops, faster and close to the machines, and slower as you go deeper into the network, all the way to the cloud. You see here the timing is microseconds in the machine level layer and milliseconds above, and up to seconds. And this idea of the distributed learning is very important. But remember, we need determinism from AI as well. And possibly digital twins are better prepared to participate in these loops, intelligent loops in the future. This is a big kind of summary of a mission critical edge, where you see a distributed set of nodes networked with this TSN, 5G, and other technologies, time sensitive technologies. And then distribution of data across the nodes is to happen with also time sensitivity, determinism, reliability in the future. This we'll see later. It's one of the areas where it's less advanced. The other topic is the orchestration of these resources and of the software, mostly now going towards microservices and containers that need also to start taking into account of the requirements of mission criticality, QoS, location, non-homogeneous hardware underneath, and so forth. And these are the things that also Tao mentioned in the 6G perspective, they need to be interworking all the way through. Otherwise, these delicate requirements will not be achieved. I already talked about this goal of the software-defined control, but the idea again is when you have deterministic networking and real-time virtualized computing, you can absorb the intelligence one level up across, say, a cell of robots, across an autonomous car made up of multiple subsystems, with the orchestration control up above. This is the way where the artificial intelligence has potential and impact, and where data and sensors can bring richness to the decisions, and collaborative decisions can be achieved. So this is the big vision that was there from the beginning, and many of you probably have seen these slides already. Let's talk about the reality here. In the last 5 years, I devoted much of my life to bringing fog and edge computing into industrial automation. And I'll talk about where this is going. On the other side is automotive is moving in the direction of edge and mission critical edge in particular. And 5G, 6G are the fundamental promise at the networking level to reduce the issue of cabling and to enable this type of intelligent control, not limited by the closeness due to the cabling problem, and the fact that the networking is not going to be quickly time sensitive in a broader way in industrial automation, and possibly in the car it is. But 5G and 6G fundamental here. So we probably know about the industrial automation pyramid. I use this picture a lot, but the concept here is there is a hierarchical control architecture, well defined, where real time is really tight close to the machines at the plant, near the plant level, where PLCs and robot controllers are. And then above, there's this supervisory level, which usually doesn't close the loop. It's just more alarm generation and other things. But this is a very crucial level. And then there's optimization and production management above. So in this hierarchical architecture, the future is really, you see it here, moving towards an infrastructure of mission critical nodes orchestrated either locally or from the cloud, where software is deployed as microservices like in the cloud. But now microservices may be time sensitive, may be safety sensitive, and so on. So this is starting to happen around the robotic cells. And I think the most important area of impact will be at the supervisory level, this level where digital twins and analytics and AI will play a role. Now, where is 5G coming into play? This is a reference to my friends at Ether, at the Open Networking Foundation. They are providing, with DARPA funding, a solution that is edge, connected edge based with private 5G orchestrated from the cloud, as you see here, but deployed at the edge. And with the local breakout, you can now start manifesting the potential of 5G in an industrial setting or similar. And you can host edge apps as well as the functionality needed for baseband processing and for user plane processing in a common mission critical infrastructure. So this is fundamental, and we are because we are trying to see the impact of a more easily deployable and mobility-friendly technology that can also be time sensitive, and that can allow to concentrate intelligence in these kind of edge nodes, and that can really transform industrial automation. This picture shows how on one hand, a mission critical node can host on one blade or multiple blades, but in a similar way, the secure communications technology, user plane functions, which need time sensitivity, performance, reliability, as well as baseband SD-RAN services that need even more RTOS, real-time OS kind of support. So, and partitioning and security next to applications that could be real time themselves, like a control of robots, the intelligence that you see here, and the safety. So this is the convergence, ultimate convergence of mixed criticality applications for the industrial with time sensitive and mission critical applications for communications. So this is the promise that we are pursuing that will make a big difference in the industrial automation space. And you see it here where you have a number of cells that with robots that could be wired or wirelessly connected to an intelligent edge node at the level of the cell, and then with private 5G go up to the next supervisory level, again, mission critical, capable of hosting a set of application, and in particular, the place where you can have the communication and 5G stack coexisting with other applications, like in the promise of Ether's technology, and the orchestration that could be remote. Now, here you can see that you can now sustain very appropriate control loops at 1 to 20 millisecond cycle times between the cell and the supervisory level, line level, or supervisory level, and even into the cell. There could be machines, motors, and other things that could be running at 1 to 5 microsecond cycle times that could also be wireless with 5G. So this is the promise, and this is the future of robot-based industrial floor that brings together mission critical edge and 5G, 6G. There is a clear use case that is becoming very relevant, which is predictive quality. Here is the case of Audi, Intel, and Nebbiolo, where you can have a simple model deployed in the welding line and at the level above. Exactly the architecture we discussed before. This is revolutionizing the quality control at Audi and will be deployed worldwide. And it requires hierarchical AI, as discussed before. Let's go a minute to the car story here. Well, I don't have a lot of time, but the automotive is moving in the same direction. As you know, the ECUs inside the car are tending to be consolidated into fewer virtualized nodes, again, supporting mixed criticality application, AutoSAR, platform manager, ADAS, AI, and communication functions. And so this is happening. It's complex, but again, the same trend is appearing here. And it's not just inside the car, it's also outside the car, where the evolution of the wireless technologies there, with the DSRC being now handicapped or eliminated, we see the importance of 5G, 6G in this context. And here we have machines, cars, people interacting, locally communicating, plus edge computing connected through 5G, 6G to the cars and people and so forth, and going up to the cloud for traffic monitoring, congestion control, and other applications, and supporting mobility and autonomy. There's a project in which we are involved in Austin that is trying to optimize the flow on preferential lanes. That is a good example of some of these elements coming together. Okay, one more slide and conclusions. Challenges. We are in the middle of the journey, and we really have to start deploying and scaling these deployments. And there's many pieces of the technology that are not fully there, but they're coming to maturity. One is the multi-core computing. We saw this mission critical computing from Intel, very promising. The evolution of virtualization for these spaces, the networking with 5G, 6G. What is not really evolving very well is the data distribution with mission criticality requirements well kept, well understood and appreciated and supported, and the orchestration that has to take into account QoS and so forth. But I would leave it with the need to work on the data distribution, middleware, protocols that allow collaboration in real time. We are far from that. And my conclusion is mission critical edge is here. The realization of the original intent is at hand. Took 10 years, but we are not far. And there is a great synergy between mission critical edge and 5G, 6G. And we see some of the benefits. However, there's much work on the technology and mostly in the early deployments and the scaling of these deployments. There's a lot of commercial challenges that we should not touch here, but we need to address those to really manifest the power of fog and edge. Thank you for your time and attention, and I'm open to your questions.
Thanks a lot, Flavio. That was an interesting talk. We have some comments as well, which say that the talk was really interesting. So thanks a lot for the talk. I think we can take. I'll summarize a couple of questions. So there is a question on software-defined networks. What role do software-defined networks play in fog/edge computing?
Oh, it's really deeply connected and embedded. We're talking about software-defined everything here. Software-defined control, software-defined networking. That is the first step that allows the networking functions to become almost like services on standard computers or capable computers. So we see that software-defined is at the heart of the evolution of 5G, 6G, and is also at the heart of the evolution of the networking industrial automation, because it's you don't want to put down too many boxes doing a router, a switch, and so on. You want to do some of those things as much as you can in software or in hardware-assisted systems of the standard type. So now networking, as we saw there, networking, control applications, data applications, and other and other services come together on a common platform and they are orchestrated using a common technology. So this is fundamental, is at the root of fog computing and edge computing.
There's one more question, Flavio, a general question. How will compute intense processes like machine learning algorithms run on the fog? And how will the resulting models be passed on to the edge nodes?
So these models are, are moved as containers or microservices. In fact, this is a very, this continuous improvement, continuous deployment is happening and is going to be using containers or microservices and be orchestrated that way. What is the other part of the question? Sorry.
Flavio, the question was, I didn't get the question, but maybe I thought I'll pose it to you. How will the models be passed on from the fog nodes to the edge nodes?
Oh, yeah. So as I answered with this idea that they will be packaged as containers and be deployed as all the other software in small components. The problem, though, is you cannot take very heavy, power-hungry AI machine learning software down to the edge. And that is also not the right place to do it. You have to bring simplified, distilled models down to the edge that also need to be explainable to the users. Particularly when you go into mission critical environments, you need something that is understood, that is open, is not a black box, also that is not predictable in its answers. So you cannot certify a stochastic easily, a stochastic machine learning algorithm, but there are now a few indications that machine learning can evolve towards a more predictable, more deterministic behavior and smaller models. So the idea is to do as much as possible in the cloud, in the learning side, also continue to learn at the edge, but with the smaller models that should move towards explainability and determinism as well, so that they can participate in control loops. Otherwise, they can't.
Okay, Flavio, thanks a lot for a great talk and answering these questions. So thank you for
have a good Happy New Year there, and I'll be on for a little while, and then see you tomorrow.
Sure, Flavio. Thanks a lot. It must be quite late. Yeah,
Bye.
thanks a lot. Yeah.
Bye.